Testing a single ground rod involves several steps. Firstly, disconnect all connected devices. This means removing all cables and appliances connected to the ground rod. Secondly, drive a temporary auxiliary ground rod. Drive a copper-clad steel rod at least 6 feet away from the ground rod you want to test. This will provide a reference point for the test. Thirdly, connect a ground resistance tester. Connect the tester to the ground rod being tested and the auxiliary ground rod. Fourthly, perform the test. Follow the tester's instructions to measure the ground resistance. Fifthly, consider acceptable resistance. A good grounding system should have a resistance of less than 10 ohms. If the measured resistance is higher, the ground rod may need to be driven deeper or additional rods may be required. Testing a ground loop rod connected system also involves a number of steps. Firstly, disconnect connected devices, disconnecting all cables and appliances connected to the grounding system. Secondly, establish a test point, creating a temporary test point by connecting a wire to a water pipe or other known good ground. Thirdly, connect a ground resistance tester, connecting the tester to the test point and to each ground rod in the system one at a time. Fourthly, perform the test, following the tester's instructions to measure the ground resistance between the test point and each ground rod. Fifthly, consider acceptable resistance. The measured resistance should be less than 10 ohms for each ground rod. If any rod has a higher resistance, it may need to be tested individually and replaced if necessary. It is important to use a ground resistance tester that is designed for testing 0 ohms resistance. If the measured resistance is too high, consider driving the rods deeper, adding more rods, or consulting with a qualified electrician for further testing and analysis. A ground resistance tester, also known as a ground tester or earth tester, is a specialized instrument used to measure the resistance of the earth or grounding system. It plays a crucial role in ensuring the safety and effectiveness of electrical grounding, which is essential for protecting people and equipment from electrical faults. The primary function of a ground resistance tester is to determine the resistance between a grounding electrode, such as a ground rod, and the surrounding earth. A low resistance value indicates a good connection to the earth, allowing fault currents to safely dissipate. A high resistance value, on the other hand, suggests a poor connection which can increase the risk of electrical shock and equipment damage. There are several types of ground resistance testers available, each employing different techniques to measure earth resistance. The most common types include the fall-off potential method, the slope method, and the clamp-on method. The fall-off potential method is the most widely used technique and involves injecting a test current into the earth through an auxiliary electrode and measuring the voltage drop between the grounding electrode and another auxiliary electrode. The resistance is then calculated using Ohm's law. The slope method is a variation of the fall-off potential method that uses multiple auxiliary electrodes to create a resistance curve, which can provide more accurate results in complex soil conditions. The clamp-on method is a non-intrusive technique that uses a specialized clamp meter to measure the current flowing through a grounding conductor. This method is particularly useful for testing grounding systems in areas where it is difficult to drive auxiliary electrodes. When using a ground resistance tester, it is important to follow the manufacturer's instructions carefully. The accuracy of the measurement depends on factors such as the proper placement of the auxiliary electrodes, the selection of the appropriate test range, and the environmental conditions. It is also important to ensure that the grounding system is isolated from other electrical circuits during the test to avoid interference. Ground resistance testers are used in a wide range of applications, including electrical power systems, telecommunications networks, industrial facilities, and residential buildings. They are essential tools for electricians, engineers, and other professionals who are responsible for ensuring the safety and reliability of electrical grounding systems. Regular testing of grounding systems is recommended to identify potential problems before they lead to electrical hazards. The frequency of testing depends on factors such as the type of grounding system, the soil conditions, and the environmental conditions. In general, it is recommended to test grounding systems at least once a year, or more frequently in areas with corrosive soil or high lightning activity. The National Electrical Code, or NEC, provides guidelines for grounding and bonding electrical systems to ensure safety. Section 250.53 G specifies the requirements for ground rods, including their size, material, and insulation depth. Ground rods must be at least 8 feet long and made of galvanized steel or copper. They must be driven into the ground so that at least 8 feet of the rod is in contact with the soil. Section 250.56 discusses the use of ground resistance testing to verify the effectiveness of grounding systems. It states that the resistance to ground should not exceed 25 ohms. If the resistance exceeds this value, the grounding system must be improved by adding additional ground rods or taking other measures to reduce the resistance. Section 250.62 provides requirements for grounding electrode conductors, which are used to connect the grounding electrode to the electrical system. These conductors must be sized according to the size of the service entrance conductors and must be protected from physical damage. Section 250.64 specifies the requirements for grounding electrode connections, which must be made using approved methods such as exothermic welding or listed connectors. These connections must be accessible for inspection and testing. Section 250.66 provides requirements for sizing the grounding electrode conductor for alternating current systems. The size of the grounding electrode conductor depends on the size of the service entrance conductors and must be large enough to safely carry fault currents. Section 250.68 specifies the requirements for bonding grounding electrodes together. If multiple grounding electrodes are used, they must be bonded together to create a common grounding system. This helps to ensure that all parts of the electrical system are at the same potential, reducing the risk of electrical shock. Section 250.70 provides requirements for methods of grounding electrode connection. Grounding electrode conductors must be connected to grounding electrodes using listed lugs, listed pressure connectors, listed clamps, or other approved means. Soldering is not permitted as a means of connecting grounding electrode conductors to grounding electrodes. It's also very important to ensure proper grounding to protect electrical systems and people. Proper grounding provides a low resistance path for fault currents to flow back to the source, causing the overcurrent protection device, such as a circuit breaker or fuse, to trip and energize the circuit. This helps to prevent electrical shock, fire, and equipment damage. Grounding also helps to stabilize voltage and reduce electrical noise, improving the performance and reliability of electrical equipment. Improper grounding can lead to a variety of problems, including electrical shock, equipment damage, and fire. It can also cause voltage fluctuations and electrical noise, which can interfere with the operation of sensitive electronic equipment. In addition, improper grounding can increase the risk of lightning damage. Driving ground rods deeper can significantly improve grounding in several ways. Firstly, deeper soil layers often have higher moisture content. Moisture is a key factor in reducing soil resistivity. Drier soils have high resistance, making it harder for fault currents to dissipate effectively. By reaching moister soil, the ground rod establishes a better electrical connection with the earth, lowering the overall ground resistance. Secondly, soil composition and density change with depth. Deeper layers may contain more conductive materials or be more compact, both of which can lower resistance. Compacted soil, for instance, provides better contact between the ground rod and the earth. Thirdly, deeper ground rods are less affected by surface soil conditions, which can vary widely due to weather, seasonal changes, and local environmental factors. Surface soil can dry out quickly or be affected by frost, both of which increase resistance. A deeper ground rod provides a more stable and consistent grounding path, unaffected by these surface variations. Fourthly, deeper ground rods increase the surface area in contact with the soil. While the relationship isn't linear, a longer rod generally has a lower resistance because it provides more pathways for current to dissipate into the earth. Fifthly, driving ground rods deeper can help in areas with poor soil conditions. Rocky, sandy, or otherwise non-conductive soils can significantly impede grounding. A deeper rod may be able to penetrate these poor layers and reach more suitable soil. Adding more ground rods to a grounding system is another effective strategy to lower ground resistance and improve overall grounding performance. Firstly, multiple ground rods provide parallel paths for fault current to flow into the earth. When resistors are connected in parallel, the total resistance is less than the resistance of any individual resistor. The same principle applies to ground rods. Each additional rod provides an alternative path for current, reducing the overall impedance of the grounding system. Secondly, multiple ground rods expand the grounding area. Each rod influences the potential of the soil around it. By spacing rods apart, you increase the overall area over which the ground system can dissipate fault currents. This is particularly useful in areas with limited space or poor soil conditions. Thirdly, multiple ground rods can improve redundancy. If one ground rod becomes damaged or corroded, the other rods can continue to provide a grounding path, ensuring continuous protection. This is important for critical systems where grounding must be maintained at all times. Fourthly, multiple ground rods can mitigate the effects of soil variations. Soil resistivity can vary significantly within a small area. By using multiple rods spaced apart, you can average out these variations and create a more consistent grounding system. Fifthly, the NEC requires or recommends multiple grounding electrodes in many situations. Section 250.53 H specifies requirements for supplemental grounding electrodes, particularly when a single electrode does not meet the required resistance of 25 ohms or less. In this case, an additional electrode is required and it must be bonded to the original electrode. Proper spacing between ground rods is crucial to maximize their effectiveness. Generally, rods should be spaced at least the length of the rod apart. For example, if you are using 8-foot ground rods, they should be spaced at least 8 feet apart. Closer spacing can result in overlapping zones of influence, reducing the effectiveness of each additional rod. Consulting with a qualified electrician is highly recommended when dealing with grounding systems for several reasons. Firstly, electricians have the knowledge and experience to properly assess the grounding needs of a specific electrical system. They can take into account factors such as the size and type of equipment, the soil conditions, and the local electrical codes to determine the appropriate grounding system. Secondly, electricians are trained in the proper installation techniques for grounding systems. They know how to drive ground rods, make proper connections, and ensure that all components are properly bonded together. Improper installation can significantly reduce the effectiveness of the grounding system and increase the risk of electrical hazards. Thirdly, electricians have the tools and equipment necessary to test grounding systems and verify that they meet the required standards. They can use ground resistance testers to measure the resistance of the grounding system and identify any potential problems. Fourthly, electrical codes and regulations related to grounding can be complex and vary from one jurisdiction to another. Electricians are familiar with these codes and can ensure that the grounding system complies with all applicable requirements. Fifthly, working with electricity can be dangerous. Electricians are trained in safety procedures and know how to avoid electrical hazards. Attempting to install or modify a grounding system without proper training can be risky and could result in serious injury or death. Electrical grounding is a critical safety measure that protects people and equipment from electrical hazards. By providing a low resistance path for fault currents to flow back to the source, grounding helps to prevent electrical shock, fire, and equipment damage. Regular testing and maintenance of grounding systems are essential to ensure their effectiveness. Grounding works by providing a low resistance path for electrical current to flow back to the source in the event of a fault. This path allows the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and de-energize the circuit, preventing electrical shock and equipment damage. Without proper grounding, fault currents can flow through unintended paths such as the human body, which can result in serious injury or death. Grounding also helps to stabilize voltage and reduce electrical noise, improving the performance and reliability of electrical equipment. There are several types of grounding systems commonly used in electrical installations. The most common types include the equipment grounding system and the system grounding system. The equipment grounding system provides a low resistance path for fault currents to flow back to the source from non-current carrying metal parts of electrical equipment, such as enclosures, conduits, and motor frames. This helps to prevent these metal parts from becoming energized during a fault, reducing the risk of electrical shock. The system grounding system connects the neutral point of the electrical system to ground. This helps to stabilize voltage and provide a reference point for the electrical system. System grounding is required for most alternating current systems, but it is not always required for direct current systems. The NEC provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure the safety and effectiveness of grounding systems. The NEC also provides guidelines for selecting and installing grounding electrodes, grounding conductors, and bonding jumpers. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of an electrical system together to create a common electrical potential. This helps to prevent voltage differences between metal parts, which can create a shock hazard. Bonding is required for all metal parts that are likely to become energized during a fault, such as enclosures, conduits, and water pipes. The NEC provides detailed requirements for bonding electrical systems. These requirements are designed to ensure that all metal parts are properly bonded together. The NEC also provides guidelines for selecting and installing bonding jumpers and bonding conductors. Grounding electrode conductors connect the grounding electrode to the electrical system. These conductors must be sized according to the size of the service entrance conductors and must be protected from physical damage. Grounding electrode connections connect the grounding electrode conductor to the grounding electrode. These connections must be made using approved methods, such as exothermic welding or listed connectors. These connections must be accessible for inspection and testing. The size of the grounding electrode conductor for alternating current systems depends on the size of the service entrance conductors and must be large enough to safely carry fault currents. Multiple grounding electrodes must be bonded together to create a common grounding system. This helps to ensure that all parts of the electrical system are at the same potential, reducing the risk of electrical shock. Grounding electrode conductors must be connected to grounding electrodes using listed lugs, listed pressure connectors, listed clamps, or other approved means. Soldering is not permitted as a means of connecting grounding electrode conductors to grounding electrodes.